Arc flash incidents that melt conduit can stem from several potential causes, each requiring careful consideration and preventative measures. Firstly, nicked wires are a primary suspect. Damage to wire insulation during installation can create pathways for ground faults or face-to-face faults. Secondly, loose connections present another significant risk. Insufficiently tightened connections introduce resistance, leading to overheating and potential arc flash events. Thirdly, inadequate grounding systems can contribute to conduit melting. Without proper grounding, a ground fault can send substantial current through the conduit, causing it to overheat and melt. Fourthly, overcurrent faults such as short circuits can generate surges of current through the conduit, resulting in rapid overheating and melting. Now, addressing the question of whether a properly grounded system can experience conduit melting when a wire grounds. Yes, it's possible. A properly grounded system provides a low resistance path for fault current. This low resistance path can result in high current through the conduit during a ground fault. The intense heat produced by this high current can melt the conduit. The age of the installation, less than 2 years, warrants examination. It suggests the possibility of a design or installation error contributing to the incident. The transformer load, which was less than 50%, indicates that the transformer was not overloaded and thus may not be the primary cause of the arc flash. The absence of vibration in the area lends support to the theory that the wires were nicked during installation. To prevent similar incidents, several measures should be implemented. 1. Ensure proper installation and thorough inspection of wires to prevent nicks or any other form of damage. 2. Regularly inspect and tighten all connections to prevent them from becoming loose over time. 3. Install and maintain an adequate grounding system. This will ensure a low resistance path for fault current in the event of a fault. 4. Utilize appropriate overcurrent protection devices. These devices are designed to prevent overcurrent faults. 5. Conduct regular maintenance and testing to identify potential faults or issues before they escalate into arc flash incidents. To delve deeper into the specifics of electrical systems and arc flash mitigation, consider the following points. Grounding systems are crucial for electrical safety. They provide a lower impedance path for fault currents, allowing protective devices to quickly clear faults. The grounding electrode system typically consists of a grounding electrode conductor, a grounding electrode, and the equipment grounding conductors. The grounding electrode conductor connects the grounded conductor of the electrical system to the grounding electrode. The grounding electrode is a conductive rod, plate, or other approved device buried in the earth to provide a connection to ground. Equipment grounding conductors provide a path for fault current to return to the source, tripping the overcurrent protective device and clearing the fault. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences between metal parts, reducing the risk of electric shock. Bonding is typically achieved using bonding jumpers, which are conductive wires or straps that connect metal parts together. Overcurrent protection is essential for preventing damage to electrical equipment and reducing the risk of electrical fires. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. Circuit breakers are reusable devices that trip when an overcurrent condition is detected. Fuses are one-time use devices that melt and interrupt the flow of current when an overcurrent condition is detected. Arc flash studies are conducted to determine the potential arc flash hazards in an electrical system. An arc flash study involves analyzing the electrical system to determine the available fault current, the arc flash boundary, and the incident energy. The arc flash boundary is the distance from the arc flash source at which the incident energy is equal to 1.2 calories per square centimeter, which is the threshold for a second-degree burn. The incident energy is the amount of thermal energy that a worker would be exposed to in the event of an arc flash. Personal protective equipment, or PPE, is essential for protecting workers from arc flash hazards. PPE includes flame-resistant clothing, safety glasses, gloves, and a face shield or arc flash suit. The level of PPE required depends on the incident energy calculated in the arc flash study. Electrical codes and standards provide guidance on the safe installation and maintenance of electrical systems. The National Electrical Code, or NEC, is a widely adopted code that provides requirements for electrical installations. The National Fire Protection Association, or NFPA, develops standards for electrical safety, including NFPA 70E, which addresses electrical safety in the workplace. Regular maintenance and testing are crucial for ensuring the continued safe operation of electrical systems. Maintenance activities include inspecting equipment for damage, tightening connections, and testing protective devices. Testing activities include insulation resistance testing, ground impedance testing, and circuit breaker testing. Now let's consider specific aspects of a 575-volt system like the one mentioned in the problem, and its implications for arc flash. A 575-volt system is considered a medium voltage system. Medium voltage systems generally have higher arc flash hazards than low voltage systems, such as 120 volts or 208 volt systems. The higher voltage can result in higher fault currents and higher incident energy levels. When working on or near a 575-volt system, it's essential to follow strict safety procedures and wear appropriate PPE. Qualified electrical workers should be trained on the specific hazards of medium voltage systems and the proper procedures for working on them safely. Overcurrent protection for a 575-volt system typically involves using circuit breakers or fuses that are rated for the voltage and current levels of the system. The overcurrent protective devices should be sized appropriately to protect the equipment and conductors from overloads and short circuits. Grounding for a 575-volt system is also critical. The grounding system should be designed to provide a low impedance path for fault currents, allowing protective devices to quickly clear faults. The grounding system should comply with the requirements of the NEC and other applicable standards. Regarding conduit selection, the type and size of conduit used in an electrical installation must be appropriate for the voltage, current, and environmental conditions. For a 575-volt system, rigid metal conduit, or RMC, or intermediate metal conduit, or IMC, are commonly used. These types of conduit provide good mechanical protection and can withstand the high fault currents that may occur in a medium voltage system. The size of the conduit should be selected based on the number and size of the conductors being installed, as well as the requirements of the NEC. It's important to ensure that the conduit is properly supported and secured to prevent damage or displacement. In addition to the points discussed above, several other factors can contribute to arc flash incidents and conduit melting. Corrosion can weaken electrical connections and increase resistance, leading to overheating and potential arc flash. Chemical exposure can damage insulation and other electrical components, increasing the risk of faults. Mechanical stress can cause wires to break or connections to loosen, leading to electrical hazards. Environmental conditions, such as temperature and humidity, can also affect the performance and reliability of electrical systems. In summary, preventing arc flash and conduit melting requires a comprehensive approach that includes proper design, installation, maintenance, and testing of electrical systems. It also requires strict adherence to safety procedures and the use of appropriate PPE. By addressing the potential causes of arc flash and implementing effective preventative measures, the risk of electrical incidents can be significantly reduced. Another key point to understand is the role of impedance in limiting fault current. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. Higher impedance in a circuit will limit the amount of fault current that can flow during a short circuit or ground fault. This is why it's important to use conductors and equipment that are properly sized for the voltage and current levels of the system. Undersized conductors or equipment can have higher impedance, which can limit the fault currents and prevent overcurrent protective devices from operating quickly enough to clear the fault. In addition to conductor size, the length of the conductor also affects impedance. Longer conductors have higher impedance, which can limit fault current. This is why it's important to keep conductor lengths as short as possible, especially in circuits with high fault current potential. Another factor that affects impedance is the type of raceway used. Metal raceways, such as rigid metal conduit or intermediate metal conduit, have lower impedance than non-metallic raceways, such as PVC conduit. This is because metal raceways provide a ground path for fault current, which helps to reduce impedance. Transformer impedance also plays a role in limiting fault current. Transformers have inherent impedance which limits the amount of current that can flow through them during a short circuit or ground fault. The impedance of a transformer is typically expressed as a percentage of the transformer's kV amp rating. Higher impedance transformers will limit fault current more effectively than lower impedance transformers. Coordination studies are conducted to ensure that overcurrent protective devices are properly coordinated to minimize the impact of faults. Coordination studies involve analyzing the time current characteristics of overcurrent protective devices to ensure that the device closest to the fault will trip first, while upstream devices will remain closed. This helps to limit the extent of the outage and prevent unnecessary tripping of upstream devices. Selective coordination is a type of coordination where the overcurrent protective devices are coordinated so that only the device closest to the fault will trip, while all other devices will remain closed. Selective coordination is often required in critical applications such as hospitals and data centers, where it's important to minimize the impact of outages. Zone-selective interlocking, or ZI, is a technique that can be used to improve the coordination of overcurrent protective devices. CSI involves using communication between overcurrent protective devices to determine which device is closest to the fault. The device closest to the fault will trip first, while other devices will be blocked from tripping. This helps to improve coordination and minimize the impact of outages. Arc-resistant switchgear is a type of switchgear that is designed to withstand the effects of an arc flash. Arc-resistant switchgear is constructed with special materials and features that help to contain the arc flash and prevent it from spreading to other equipment. Arc-resistant switchgear is often used in applications where arc flash hazards are high. Infrared scanning is a technique that can be used to detect hotspots in electrical equipment. Infrared scanning involves using an infrared camera to measure the temperature of electrical components. Hotspots can indicate loose connections, overloaded circuits, or other problems that could lead to an arc flash. Power quality monitoring is a technique that can be used to detect power quality problems such as voltage sags, voltage swells, and harmonics. Power quality problems can damage electrical equipment and increase the risk of arc flash. Regular power quality monitoring can help to identify and correct power quality problems before they cause damage or increase the risk of arc flash. Transient voltage surge suppression, or TVSS, devices are used to protect electrical equipment from voltage surges. Voltage surges can damage electrical equipment and increase the risk of arc flash. TVSS devices can help to protect equipment from voltage surges and reduce the risk of arc flash. Finally, consider the importance of documentation and record keeping. Accurate and up-to-date documentation of electrical systems is essential for safe and efficient operation. Documentation should include single-line diagrams, equipment specifications, overcurrent protective device settings, and maintenance records. Regular audits of electrical systems can help to identify potential problems and ensure that the systems are operating safely and efficiently. Audits should be conducted by qualified personnel and should include a review of documentation, a visual inspection of equipment, and testing of protective devices. Furthermore, employee training plays a vital role. Electrical safety training should be provided to all employees who work on or near electrical equipment. Training should cover the hazards of electricity, safe work practices, and the use of personal protective equipment. Refresher training should be provided regularly to ensure that employees are up to date on the latest safety procedures. Emergency response planning is also essential. An emergency response plan should be developed to address potential electrical incidents such as arc flash, electrical shock, and electrical fires. The plan should include procedures for notifying emergency personnel, evacuating the area, and providing first aid. Regular drills should be conducted to ensure that employees are familiar with the emergency response plan. The investigation of electrical incidents is crucial for preventing future occurrences. When an electrical incident occurs, a thorough investigation should be conducted to determine the cause of the incident and identify any contributing factors. The investigation should include a review of documentation, interviews with witnesses, and an examination of the equipment involved. Corrective actions should be taken to address the root cause of the incident and prevent similar incidents from occurring in the future. Remember, the prevention of arc flash and conduit melting is an ongoing process that requires a commitment to safety from all levels of an organization. By implementing the measures described above, the risk of electrical incidents can be significantly reduced, creating a safer working environment. Also consider the role of advanced technologies in arc flash detection and mitigation. Arc flash detection systems are designed to detect the light and pressure waves produced by an arc flash and quickly trip the overcurrent protective devices to minimize the duration and severity of the arc flash. These systems can significantly reduce the incident energy and prevent equipment damage. Solid-state relays are increasingly used in electrical protection schemes. Solid-state relays offer faster response times and greater accuracy compared to traditional electromechanical relays. This can improve the coordination of overcurrent protective devices and reduce the impact of faults. Smart grid technologies are also playing a role in arc flash mitigation. Smart grids use sensors and communication networks to monitor the condition of electrical equipment and detect potential problems before they lead to arc flash. This allows for proactive maintenance and can prevent electrical incidents. Consider the specific types of electrical conductors used in a system. The type of conductor used can affect the impedance of the circuit and the potential for arc flash. Copper conductors have lower impedance than aluminum conductors, which can result in higher fault currents. The insulation rating of the conductor is also important. Conductors with higher insulation ratings can withstand higher voltages and reduce the risk of insulation breakdown, which can lead to arc flash. Also consider the derriting of conductors. Conductors must be derrited when they are installed in conduit or cable trays or when they are exposed to high ambient temperatures. Derriting reduces the ampacity of the conductor and can increase the impedance of the circuit. Now, let's talk more about the importance of regular inspections. Regular visual inspections of electrical equipment can help to identify potential problems before they lead to arc flash. Inspections should include checking for loose connections, damaged insulation, and signs of overheating. Thermographic inspections, as mentioned earlier, can also be used to detect hot spots that are not visible to the naked eye. Detailed record keeping is paramount. Maintaining detailed records of inspections, maintenance, and testing is essential for tracking the condition of electrical equipment and identifying trends. Records should include the date of the inspection, the findings, and any corrective actions taken. Finally, don't underestimate the importance of communication. Open communication between management, engineers, and workers is essential for creating a safe working environment. Workers should be encouraged to report any potential hazards or concerns to their supervisors. Regular safety meetings should be held to discuss electrical safety issues and reinforce safe work practices. By fostering a culture of safety and promoting open communication, organizations can significantly reduce the risk of arc flash and other electrical incidents. I will dive into some deeper technical topics as well. Firstly, let's discuss the concept of bolted fault current versus arc fault current. A bolted fault is a direct short circuit between conductors of different phases or between a conductor and ground. The fault current in a bolted fault is limited only by the impedance of the circuit. An arc fault, on the other hand, involves an electrical arc between conductors. The arc resistance limits the fault current to a value lower than the bolted fault current. The arc fault current is typically much lower than the bolted fault current, but it can still be high enough to cause significant damage and injury. Secondly, consider the arc flash protection strategies. Current limiting fuses are a type of overcurrent protective device that can quickly interrupt high fault currents. Current limiting fuses can be used to reduce the incident energy in an arc flash event. Arc flash relays are designed to detect the light and pressure waves produced by an arc flash and quickly trip the overcurrent protective devices. Arc flash relays can be used to reduce the duration of the arc flash and the incident energy. Remote racking systems allow workers to remotely operate circuit breakers and other electrical equipment. Remote racking systems can be used to reduce the risk of exposure to arc flash hazards. Thirdly, let's talk about the selection of appropriate PPE for arc flash protection. The selection of PPE should be based on the incident energy calculated in the arc flash study. The incident energy is typically expressed in calories per square centimeter. PPE is available in different arc ratings, which indicate the amount of incident energy that the PPE can withstand. The arc rating of the PPE should be greater than or be equal to the incident energy calculated in the arc flash study. Fourthly, the importance of properly maintaining and calibrating electrical testing equipment should not be overlooked. Electrical testing equipment, such as multimeters, clamp-on ammeters, and insulation resistance testers, should be properly maintained and calibrated to ensure accurate readings. Inaccurate readings can lead to incorrect decisions about the safety of electrical equipment and can increase the risk of arc flash. Fifthly, the role of harmonics in electrical systems should be understood. Harmonics are distortions in the sinusoidal waveform of alternating current. Harmonics can be caused by nonlinear loads such as electronic equipment and adjustable speed drives. Harmonics can increase the current in electrical conductors, which can lead to overheating and potential arc flash. Now let's look at the specific requirements of the NEC related to arc flash safety. NEC section 110.16 requires that electrical equipment be marked with a warning label indicating the arc flash hazard. The warning label should include the nominal voltage, the arc flash boundary, and the required PPE. NEC section 130.5 requires that a written electrical safety program be established and implemented. The electrical safety program should include procedures for identifying and evaluating electrical hazards, selecting appropriate PPE, and training employees. NEC section 230.95 requires that ground fault protection be provided for service equipment. Ground fault protection is designed to detect ground faults and quickly trip the overcurrent protective device. Finally, the significance of adhering to manufacturers' recommendations for the installation, operation, and maintenance of electrical equipment should be considered. Manufacturers' recommendations are based on extensive testing and experience and should be followed to ensure the safe and reliable operation of electrical equipment. Deviations from manufacturers' recommendations can void warranties and increase the risk of electrical hazards. In summary, preventing arc flash requires a comprehensive approach that includes proper design, installation, maintenance, testing, and training. By understanding the hazards of arc flash and implementing effective preventative measures, the risk of electrical incidents can be significantly reduced. Also, consider some of the newer technologies emerging in arc flash protection. Arc flash mitigation systems are designed to automatically reduce the incident energy in an arc flash event. These systems use advanced sensors and control algorithms to detect an arc flash and quickly trip the overcurrent protective devices. Some arc flash mitigation systems can also inject a fault current to quickly clear the arc flash. Solid-state circuit breakers are a new type of circuit breaker that uses solid-state technology to provide faster and more reliable protection. Solid-state circuit breakers can trip much faster than traditional electromechanical circuit breakers, which can reduce the incident energy in an arc flash event. Wireless monitoring systems are used to monitor the condition of electrical equipment remotely. Wireless monitoring systems can detect potential problems such as loose connections, overheating, and insulation degradation before they lead to an arc flash. Predictive maintenance techniques are used to predict when electrical equipment is likely to fail. Predictive maintenance techniques can help to prevent unexpected equipment failures, which can reduce the risk of arc flash. Augmented reality is used to provide workers with real-time information about electrical equipment. Augmented reality can help workers to identify potential hazards and perform maintenance tasks safely. Drones are used to inspect electrical equipment in difficult-to-reach locations. Drones can be equipped with cameras and sensors to detect potential problems such as loose connections, overheating, and corrosion. Digital twins are virtual models of electrical systems. Digital twins can be used to simulate different operating scenarios and identify potential hazards. Furthermore, consider the integration of arc flash protection into building automation systems. Building automation systems can be used to monitor a condition of electrical equipment and detect potential problems. Building automation systems can also be used to control the operation of electrical equipment to reduce the risk of arc flash. For example, a building automation system can be programmed to automatically de-energize equipment before workers perform maintenance tasks. The implementation of arc flash safety programs should also be adaptive. Arc flash safety programs should be reviewed and updated regularly to reflect changes in technology, standards, and best practices. The effectiveness of the arc flash safety program should be evaluated regularly to identify areas for improvement. And lastly, the role of leadership in promoting arc flash safety must be emphasized. Leadership should demonstrate a commitment to arc flash safety by providing resources, training, and support. Leadership should also hold employees accountable for following safe work practices. By creating a culture of safety, organizations can significantly reduce the risk of arc flash and other electrical incidents.